Hello. I decided this morning, so good morning, you're about to see me in about a half an hour. I decided this morning that I wanted to do a small change in plans, and I wanted to give this to you guys as a video rather than a mini lesson in a live stream or a meet that you couldn't pause, you couldn't rewatch, and you couldn't kind of get yourself back into. So here we are. We're going to go the video format instead. I just want to give you guys a bit of an intro, nothing too crazy, on systems of equations. I know that you guys have worked with actual linear equations in the past, so we're going to just kind of ramp that up a small notch. We're going to keep going forward with our equations, but now we're going to be working with two equations at a time rather than just with one. So some of the things that you guys know about linear functions. We'll talk about this later on too. I'll give you kind of like this will be your way to get in and out of chat situation. So like what are some of the things that you know about linear functions? You know that they form that straight line. You know that their exponents have a 1, so it would be x to the first power, but we don't see that 1. You know that we can graph them a couple of different ways. You can graph them with slope-intercept form. You can graph them in point-slope form, or you can graph them from standard form. All of those are things that you guys have done. So those are some of the things that you know about linear functions. And I just want to shoot out and remind you guys that it is true that on a line, if you were to graph a line, every single point along that line, even the ugly fractions and the decimals kind of in between the tick marks of your grid, every single point on that line is considered a solution to that line. We talked about solutions a lot when we talked about inequalities last week, and we had solutions that were on the line or solutions that were in the shaded areas. This is just your little friendly reminder that every point along the line on that line is a solution to that function, no matter how ugly the decimal or fraction is. So looking here at this, we can take our little drawing tool here as well. We're going to talk about some of the solutions to this function. Two obvious solutions to this function are your two green dots here. So you have a solution here at 0. I am writing this with the mouse. At 0, 1, or you have a solution here at 2, 3. Those are points on your line. Anything other point on your line, you have a point over here at looks like -3, -2. That is a solution. You have a point here at -5, just about -4. Any of these fractional points, these decimal points in between, any single point you can imagine on this line is going to be a solution to this function. So what do we call these types of lines? Two lines that are never going to intersect. They're going to run just like this next to each other. We talked about these when we were graphing earlier on. We talked about something special about their slopes, which we're going to get into in just a second as well. These two lines, there's something special about them. They are parallel lines. They run right next to each other and they will never intersect. And if you were to go through here, I'm going to give you these notes slides in your Google Classroom so you can go in here if you want some practice and write the equation of these two lines. You can write them in any of the formats you want. I recommend slope-intercept form because you do have a y-intercept obviously for each of them, and you can use the picture to calculate a slope between the points. You will notice that those two equations, because they are parallel lines, just like we talked about when we talked about parallel lines a while back, they will have the same slope. They run at the same slope, they run at the same steepness, so that they will never intersect. And these two lines, we talked about this also when we talked about parallel lines. These two lines that intersect at a 90-degree angle are what we call perpendicular lines. they meet like this. They meet at 4 right angles. That's what that little symbol, in case you forget that little red square in here, that symbol does mean that these are at a right angle. And you can do that same thing, get your practice in on writing your equations in slope-intercept form. And you'll see that, remember, we talked about the two equations. The two slopes of a perpendicular set of lines are opposite reciprocals. So if one was negative, it becomes positive, and the fraction flips upside down. So you can go in here and we can name some of the solutions to these functions. Let's do green because they aren't the same color here. So any of these points along this red line are going to be solutions, including this magical point right here. I'm going to do of 0, 0. That's the big obvious point that it runs into. These little fractions here, this looks like -1, -3. It looks like -4, -6 is a point. All of these are solutions to the red line. We can do that same thing here. You'll see these are perpendicular. I have a 2 as the slope here, and a -1/2. Those are opposite reciprocals. Any of these points on this blue line, including here where they seem to run into each other at 0, 0, are solutions to the blue function. So there's different ways that these things can happen. If I were to graph two lines on the same chart, just like we did, we had two graphs on the first one where we had parallel lines. I just had two lines where they were perpendicular. I can graph two lines on any grid, and those will be called a system of equations because there's two lines in that system. There are two lines on that grid. So we have to figure out how many different ways can or cannot two straight lines, two lines cross. So we already kind of just looked at option number 1, scenario number 1, where the two lines are parallel and they run right next to each other. You'll see up at the top it says that a system consisting of two parallel lines has no solution. So there is no solution here because a solution to a system of equations, so two lines running next to each other, the solution here is any point that they cross or that they touch. In parallel lines, these two lines are never going to cross. So their systems, their solutions are never going to be the same. So there is no solution to this system. They're never going to touch. These two lines are just going to stay running parallel next to each other with no crossing. Option number 2, obviously, is that your two lines can cross at some point, at some angle. Doesn't quite matter which. You've got some examples down there. Your two lines can cross at any one point. In this case, they cross at my wrists. So if I were to graph two lines on the same grid, on the same plane, they cross at one point. That point where they meet, so the point at my wrists, or the point here at where these two meet, let's go backwards, the point where these two meet, the point where these two meet, that point where those two lines cross is your solution. It has one solution, one point that they cross to your system. We're going to talk a little bit more about this when you guys practice tomorrow with graphing. Or there is that last strange scenario where two lines can be graphed on top of each other. They're technically the same line. They might have had slightly different formulas, but they do graph directly one on top of the other. And if I said that every single point that they touch is a solution, well, these are constantly touching. They touch at all points. So that means that there is infinite solutions or an infinite amount of solutions. Some people say infinitely many solutions. All of those are the cases in which these three will touch. So I want to kind of leave you with your definition, making sure that this gets down. I know that my little camera is slightly in the way at this moment in time. Nope. Okay. I can't, unfortunately, move me. So you'll have to deal with me. When you get these slides, you'll be able to get this spot as well. but it does say when they do touch, the point or points at which they touch are the solutions. That's what we were just talking about. A system of linear equations is when two lines work together or they're graphed on the same coordinate plane. You might have that red line, the blue line, and if they touch, that point where they touch is a solution. We discussed that there are the three different situations, the three scenarios for how they may touch. Let me just make myself disappear for a second. There we go. Y'all still hear me, just won't see me. Your three different situations where they have intersecting lines and they meet at exactly one solution. They may be the same line, but they'll have infinitely many solutions or an infinite number of solutions. Or they may be parallel lines where they don't have a solution because they're never going to meet. So tomorrow, what we will do, you won't get these quite yet. I'll add them into your slides tomorrow so that you can see them. You've got these couple of practices that we're going to do tomorrow with you so that you have a little bit of oomph on where you are headed for that. And we'll get some practice in graphing. So one of the ways to solve, let's stay here, so you can see the whole thing. One of the ways to solve a system of linear equations, as you know, is going to be graphing. When we graph them on the same plane or on the same grid, we'll be able to tell right away just by looking at the picture how many solutions that system has, or if it even has solutions to begin with. So that is our best case scenario. We will be able to graph them and decide right then and there that we are situated and that we have a solution, or that we have infinite solutions, or that we have no solutions. Should you need to write any of that down or see it, welcome to go back, pause, rewatch me, and I will be ready to rock and roll with you guys tomorrow.